All right, here we go. Physics reaction video number 46. Did a search this time for AP Physics HW instead of spelling out the word homework. And did a filter of in the last week and found this. So I don't know what quest means, but apparently it's problems 11, 12, and 13. Looks like, sort of kinematics, mechanics problems here. So here we go.
Hi, ladies and gentlemen, this is Miss Quackenbush, and I am going to take you through homework 8, problems 11, 12, and 13. In this problem, we actually start out with this little blocks compressing this spring by an amount, in my case, equal to 5.2 centimeters. I'm not actually going to use any numbers in my solution, but I'm going to go ahead and call that.
So she says she's not going to use any numbers in her solution. So I'm guessing that means to sort of show it algebraically, and students could maybe put it into the calculator at that point. A couple of things about this diagram that I think are interesting. I actually think this is hard to read. I think the 9.81 is easy and recognizable, but this, it's so interesting, right? Like whoever types it, and maybe she did, I'm not sure. It's interesting to use the typesetting to put the number like that. When I'm at conferences and looking at people's graphs, I'm constantly trying to figure out what the y-axis is. And I find it's really interesting that people do this for the visual, even though if you were to make this horizontal, like maybe right here, the arrow indicates the direction and I could more easily read what's there. So just a issue about typesetting. So it looks like this thing gets compressed and then it springs off and then I don't know what this 1 meter section is. I don't know, maybe that's friction or something, and then it falls off. So that's pretty interesting. Also, I just wanted to point out that her cursor with this, I don't know, black thing going on here is very noticeable. Also, it has the yellow sometimes, so you can really see where she's talking, and quite seamless being able to write right onto the page. So I'm guessing this is some sort of PDF annotator. Can we see? Trying to see what it says. Oh, these are the downloads. Looks like this is some sort of PDF annotator, maybe, or something. Since it's screencast-o-matic, I think that means this is a web page. No, I can't remember. Maybe screencast-o-matic can do any application that's open. All right, cool. I'm just going to back up a tiny little bit.
Any numbers in my solution, but I'm going to go ahead and call that. Do I want to call it delta x? Yeah, I'm going to go ahead and call it delta x, and I'm going to actually call this d, just because sometimes I like to call both of those delta x. Now, you want to go ahead
Awesome.
and make sure that you convert that into meters, and so
Of course.
there are 100 centimeters in a meter, so if I divide through by 100, I get 0.052 meters.
So I thought that was really interesting how she did that conversion. She said, well, there's 100 centimeters in a meter, so boom. So I know that sometimes people really like to sort of draw it out literally 1 meter over 100 centimeters. Something that I'll do sometimes is I'll say, let's see, is it big or small, right? Like I know I need to move the decimal place. I just need to figure out which way I need to move it. And let's see, 5.2 centimeters. So that's way less than 1 meter. So I must have to move it to the left. So I'll ask you guys, like, for all these conversions, what do you find is useful from two perspectives? The scaffolded perspective, like making sure they know how to do it. And then on the far other end of the spectrum, unscaffolded, like, hey, they should be able to do this. What tools are you hoping to give them so that they can just handle this stuff? Let's see, this is in meters already. This is in meters already. This is in meters already. And this is in meters per second. And of course, this doesn't have any units. So I guess we're good to go here.
And I'm also going to convert this by dividing through by 1,000 to kilograms. And so
didn't notice that one.
Mass in that case is 0.553 kilograms. And I'm just saying that because we want to make sure that all of our units are going to be in newtons and meters and seconds, because those are our standard SI units. Now, what happens in this problem, again, is this block is compressing this spring by an amount equal to, in my case, 5.2 centimeters. And it's held at rest at that point. I'm going to go ahead and call that point when it is compressing that spring point A. And then it's going to slide across, and we're just seeing it at an intermediate position. And then it reaches this little patch, and this little patch has some friction on it. And then it goes ahead and only while it's on that patch, how convenient, it has some friction, but then we're going to go ahead and it's going to slide off the table and it becomes a projectile. And so I'm going to go ahead and
I love that.
also label the point where it just is leaving the table point B. Okay. And
So that was so interesting when she said how convenient, right? So the real world has friction all over the place. This makes this problem totally doable by saying, oh, it's ice everywhere else except for this one spot. So I really loved how she called attention to that, right? Like she knows what's going on, and she likely guesses that her students know what's going on. So I think that's super, super cool. I love the scaffolding that she's doing here, labeling the points. My guess is, I'm not sure how far along she's going to go, but my guess is as she's doing calculations, she could say at part A, da, 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 at B, da, 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 da. So she'll be able to say different things at those different things. So at those different points. So really scaffolding that well is pretty cool. Thinking, I always think about this with springs, right? Like, are the students convinced that when the spring uncoils, wonk, I guess it's more like this, wonk, right? That right at that moment, the mass leaves the spring, and so it's somehow it's not connected. It just pushes it in. When it goes, at what point is the mass for sure going to be disconnected from the spring? We usually say it's right at its normal length, but of course the spring's going to keep going, right? Because the spring has mass. The spring's going to overextend also, but by then let's assume that the mass is disconnected. Another way to say that is that the spring can only push the block. It can't pull the block because it's not connected.
so this is a scenario where there are external unbalanced forces that are acting on this, or as we can say, there are some non-conservative forces, mainly friction, that is doing some work on this block. So from the point A where the spring is compressed to point B where this block is sliding off of this table, mechanical energy is not conserved. But we can go ahead and write this expression. Remember that the total mechanical energy that we start out with, kinetic energy plus elastic potential energy plus gravitational potential energy. Uh-oh, here comes my cat. She's looking for trouble. Sorry. That
Awesome.
all of this energy that we start out with, plus the work done by non-conservative forces,
Ooh,
is
I
going to
like
be
that.
equal to the kinetic energy and the gravitational potential energy and the elastic potential energy that we end up with. Okay,
Love it.
so
That's awesome.
this is our more generic expression for conservation of mechanical energy, taking into account a situation where we have non-conservative forces, in this case, friction, doing work. So this is all I'm going to say really.
So it's interesting, right? I think I might have been lazy and just gotten rid of this one here because there, we're done with the spring by the end of the problem. But I think it's super great to really have all of it on both sides, and if it happens to be zero, then awesome.
Forces, in this case, friction, doing work. So this is all I'm going to say. Really, this is not just the initial. This is going to be at point A, and this
Cool.
is at point B. Look, I didn't have to
Oh,
get my
cool.
eraser out for that. And here's the thing, at point A is when my spring is compressed, so I don't have any kinetic energy. I'm just holding that block in place, and then I release it, so it has no kinetic energy. At point B, there's no elastic potential energy. And then you might notice that the gravitational potential energy at points A and point B.
So I'm thinking again about the value of video, right? So if all the student had was this piece of paper when she was done, they might be like, "Huh, what happened?" But what I love is her stroke through the kinetic energy and the strokes through the elastic potential energy are not in the same direction. And so often what people will do if things are canceling, they'll have the cancel stroke be in the same direction, like, this is equal to that, so we'll cancel it. So having her literally a different way to say that this is zero is helpful, I think. But again, with video, if you watch this video, you could not possibly be confused about that. I am curious to see where she defines the zero of gravitational potential energy. I feel like a lot of students always choose the lowest point. I feel like because most of this problem is up on the shelf, maybe we should define this to be the zero. But regardless, these two are going to cancel. They're equal to each other. So let's see where she sets the zero of gravitational.
Notice that the gravitational potential energy at points A and point B are the same. And because they're the same, whether it's 10 or 5 or whatever it is, it's on both sides. It's added to both sides. So I can actually get rid of that as well. And so what I end
Cool.
up with is a much cleaner expression for conservation of energy. The work done by non-conservative forces, I also could call that the work done by friction, is going to be equal to the kinetic energy
Love it.
that this block has right before it slides off the table. And that's all great, but you're gonna start to dig into this and you're gonna be like, wait a minute, we don't have enough information yet. But um, I'm going to go ahead and say, okay, well, this is going to be 1/2 of our K value, which you're given a K value. Oh, no, actually, we're supposed to find this K value. That times your
Ooh, that's cool.
compression squared plus the work done by friction. The work done by friction, I'm going to go ahead and
So I'm just going to pause. The work done by friction is so interesting in this problem, and I've talked often about work energy theorem versus impulse momentum theorem. And work energy only cares about distance, doesn't care how long it takes. So we actually don't need to know much about the dynamics of the particle in this 1 meter stretch of so-called frictionless space. That's awesome because we're able to say, oh, well, who cares how fast it's going? I can tell you how much work it did. And so she's going to be able to write something down for this. And then, wow, this is such a cool problem because we actually probably don't know a whole lot about this. But because we know this number and this number, we're going to be able to figure all of this out. So you're going to have to build it all up and then pull it all back again because it sounds like this is the unknown in the problem. That's pretty cool. Just quickly, so when I give quizzes, so typically what I'll do in a class like this is I'll assign 4 problems in a night and I'll say, hey, these 4 problems really hit the highlights of what we learned today. Here you go. And then the next day I'll roll a 4-sided die because I actually found I was really struggling with grading homework when I couldn't quite tell that it was their work, whether they had gotten it from some, online site or worked together with each other. And I was struggling because I really wanted them to use resources like online sites and each other, but I wasn't sure how to do the assessment piece. So I started doing these daily quizzes. So assign 4 problems and then roll a 4-sided die in class. And whatever problem came up, they had to then do that with, all their notes and stuff aside. I typically did it in 10 minutes. And of course, to do a problem like this in 10 minutes, you really have to understand it, right? Normally, a problem like this is going to take you, I don't know, half an hour. But if you've worked it the night before and really read it and thought about it, you should be able to do it the next day in 10 minutes. But the other thing that I'll do sometimes is I'll say, oh, well, let's just turn this thing inside out. How about I give you K and I don't give you D? And I would ask my students after I rolled the die, I'd say, well, is that doable? Does that make it a doable problem? And they'll say, yeah. So, well, what if I gave you K and didn't give you this and didn't give you this? And students say, well, gosh, I was working this problem last night. I'm pretty sure we need all of that information. There's basically only one unknown that we can handle here. The other thing that happened when I rolled a 4-sided die is that somebody always groaned, right? Either I would groan like, oh man, that's the easy one, or not the whole class. A subset of the class would groan and say, oh man, that's the one I didn't understand. And what was fascinating about this is that the students would come to my office hours not to just get the problem done, but to understand. And my office hours would be like, well gosh, what if tomorrow you decide that this thing is 2 meters long, or what if the mass change, or what if we don't know the mass? You know what I mean? And they would try to figure out all of the interconnections among the parameters so that if that problem came up the next day for the quiz, they were ready for it. So turned out that I cut my grading by a factor of 4 because I only had 1 problem to grade per student. And I really felt that they were the night before trying to learn the material as opposed to just getting the right answer down. So I love doing these problems algebraically because the students can see the whole thing written out and say, oh, okay, let me think. All right, yeah, if I don't know K, this all works together. Because that's what's going to happen here, right? When she does the second part, all of the parameters are going to be in there. And we can ask, well, which of these do you have to know and which don't you need to know? The other thing that I would do is I would change the numbers, right? Like, because I didn't want students to just write a number at the bottom. I would just change the numbers. And actually what I started to do is I'd say, okay, you guys, I need 1, 2, 3, 4, 5, 6, 7 numbers. So just start shouting some numbers out. People would say 1,000, and I would have this maybe drawn on the board, and I would say, okay, well, let's say that the acceleration is 1,000. Someone else would say negative 7.2, and I'd say, okay, well, then this distance is negative 7.2, and I would write them all down, and I would turn around and I would say, okay, is this a realistic problem? Are we expecting a funky answer, a crazy answer, a normal answer, an answer that violates laws of physics? And someone would say, I have no idea how to deal with a negative 7.2 meter section of friction, right? Like, oh, well, okay, should I change that? And so what I found was those conversations before I actually started the quiz were super, super valuable to understand these relationships. All right, long diatribe over. Let's get back to it here.
Plus the work done by friction. The work done by friction, I'm going to go ahead and set that up over here. That's going to be equal to the friction force times the displacement. In my case, that's going to be 1 meter, times the cosine. Friction acts to the left while this block is moving to the right, so that's going to be a cosine of 180 degrees, which
Love it.
You might remember that we can go ahead and substitute that in with a -1. And then so all I have to figure out is what is that friction force. That friction force is going to be the coefficient of friction times the normal force, where the normal force is going to be equal to gravity in that case. So all of that times 1 meter, in my case, times -1 is how I would solve for the work done by friction. So I have this.
I really love, oh shoot, you can't see it, this cosine of 180, right? So students should know that the frictional force is constantly going to be taking energy away. And so we fully expect the non-conservative work to be a negative sign. So by you could just say that, hey guys, it's going to be negative. Or you can really drive home this idea of the cosine of the angle. And so I really, really like that.
This expression for elastic potential energy plus the work done by friction, which will be negative. Okay, so when you put it into the equation, you're actually going to be losing energy, which makes sense. That's taking the energy that we have and turning it into thermal energy. And all of that's going to be equal to the kinetic energy that you have right before this thing leaves the table. So if you're looking at that equation right off, we are looking for K. We have everything else, or we can solve for everything else, except we don't have this V. And so if we've only got one equation and we have 2 unknowns, we've got to do something else. That's where this projectile part.
So yeah, that's actually a good way to say it. There's 2 unknowns. So if I'm doing this as a quiz, obviously this problem is doable if you don't know K and you don't know V. But can you actually choose any 2 and call them the unknowns, right? Like let's say you didn't know this and you didn't know this, or you didn't know this and you didn't know this, right? That's what I was driving my students to do the night before, is to really think about, do we know everything? And we're going to see it here as she start. Well, I'm not sure if there's going to be enough time to finish it, but let's see what happens here.
Part of the problem comes in. Okay, and so to figure out how fast it's traveling when it leaves this table ledge, we're going to remember that this is a projectile and it's actually a horizontally launched projectile. So I'm going to go ahead and make my little T-chart for my horizontally launched projectile. I'm going to remember for any horizontally launched projectile that the initial vertical velocity is 0. I'm going to remember that the acceleration is the acceleration due to gravity. And I also have the vertical displacement in my particular problem is given a value of 1.9 meters. Yours will be different, so make sure to look for that. And then on the horizontal side, we have we've got the horizontal displacement. And that's all we've got. And what we really need to solve for, that we want to put into this equation, is going to be that horizontal velocity that it's leaving the edge of the table with. So that's what we're trying to solve. And you might remember, and I like to just go ahead and write this stuff on here just to hopefully, solidify it in your brain. I need 3 pieces of vertical information. I have 3. But I'm really trying to solve for this horizontal piece. I need 2. I only have 1 piece. So what I'm going to do is I'm going to solve for time, and then I'm going to pull the time over here.
That's cool.
That's going to help me solve for that.
Love that. Man, that was cool.
Velocity, which is going to be our velocity that we plug into that.
Man, that was cool.
And so what equation has all of those vertical components in it? It's this one. I don't want to say it's my favorite. It's not my favorite, but it's one of them. They're all my favorites. Okay, and because the initial velocity is 0, it just is going to become, in my case, 1.9 meters is equal to a half of 9.8 meters per second squared times t squared. That means that t is going to be equal to the square root of 1.9 times 2 over 9.8. And I got a little sloppy not putting my units in there, but that's how you solve for your time. Once you have your time, you're going to take that over to the horizontal equation, and you have one and only one horizontal equation because the horizontal velocity is constant. And you have your horizontal distance that was traveled, and you're looking for Vx. So if you take that horizontal distance and divide by the time that you just calculated, you'll get that velocity, and you'll substitute that velocity back into this equation, and you have everything else that you can solve for k. And then, you know, in having done that, we also solved for the speed of the block when it left the track. So the last thing you need to solve for is the total speed of the block when it hits the ground.
So I'm just going to stop right there. So that last one is just like an extra, hey, let's calculate something more. Wow, super, super cool stuff in this problem. Love this 3 and 2 stuff. Man, that was really, really cool. Loved this description very, very carefully of what was happening with the energy. Just lots of really cool stuff in this problem. Really, really loved how she worked it and she scaffolded it. All right, everybody, well, have a great day. And remember, physics teachers are awesome.